Hello everyone, my name is Jie Wang. In this talk, I will introduce TSSOS, a Julia library to explore sparsity for large-scale polynomial optimization. TSSOS aims to solve the polynomial optimization problem of this form, where the objective function and constraints are well defined by polynomials. In general, this problem is non-convex NP-hard. The well-established moment-SOS hierarchy allows us to approximate, retrieve the global optimal optimizers while solving a sequence of semi-definite programs with increasing sizes. The moment-SOS hierarchy is illustrated by the following diagram. The left side corresponds to the moment relaxation, and the right side corresponds to the dual SOS relaxation. By increasing the relaxation order D, we obtain tighter and tighter lower bounds for the global optimal F star. To improve the scalability of the moment-SOS hierarchy, it's crucial to reduce the size of STPs arising from the moment-SOS hierarchy by exploiting structure of the problem. A first option is to explore correlative sparsity. By considering the correlative sparse pattern graph, we partition the set of variables into a type of subsets. Then we construct moment localized matrices with respect to the variables involved in each maximum click of the correlative sparse pattern graph. Besides correlative sparsity, we can also explore turn sparsity. By contrast with the correlative sparsity concerning variables, turn sparsity, tree sparsity, and turn level. For each moment localizing matrix, we iteratively construct a ascending chain of graphs. Then for each k, which is called the sparse order, we may consider the following sparse moment relaxation. And a consequence, we obtain a two-level hierarchy of lower bounds for the global optimal F star as illustrated by this diagram. By increasing the relaxation order D or increasing the sparse order K, we then obtain tighter and tighter lower bounds for F star. For large-scale polynomial optimization problem, a natural idea is to combine correlative sparsity with the turn sparsity to further reduce the size of STPs arising from the moment-SOS relaxation hierarchy. The combination splits into two steps. Step 1, partitioning the variables with respect to the maximum clicks of the correlative sparse pattern graph. Step 2, for each subsystem involving variables from one maximal click, applying the iterative procedure to explore turn sparsity. There are two types of quarter extensions that we can choose from in TSSOS for turn sparsity. One is the maximal quarter extension. The other is approximately smallest quarter extensions. If the problem involves binary variables, this can be used to reduce the size of STPs. If the problem involves equality constraints, this can be also used to reduce the size of STPs by computing the nominal bases. TSSOS supports merging PSD blocks for which there are a large number of overlaps. It's also possible to extract the approximate solution and then refining it by the local solver apoped in TSSOS. So far, we consider the usual polynomial optimization, which involves commuting variables over the real numbers. But TSSOS also supports complex polynomial optimization and noncommutative polynomial optimization, including eigenvalue optimization and trace optimization. By the corresponding moment-SOS hierarchies, TSSOS is freely available on GitHub. It depends on the following packages: multivariate polynomials, jump, net graphs, smooth graphs, quarter graph, and semi-algebraic access. Besides, TSSOS requires a STP solver, which can be Mosaic, STP3, or Cosmo. The usage of TSSOS is quite simple. First, you can use the package dynamic polynomials to define your POP. First, you define the objective function, and then you define the equality constraints and the equality constraints. Then you choose a relaxation order, and you can solve it with using TSSOS first, which solves the first step of the TSSOS hierarchy, and using TSSOS higher, which solves higher steps of the TSSOS hierarchy. If you wish to explore also correlative sparsity, then you can use CS TSSOS first and CS TSSOS higher. For large-scale polynomial optimization problems, it's more efficient to define the supports and the coefficients directly. For instance, the monomial x124 x2 squared can be represented by this vector. Then you define the support array of the POP, and then you define the coefficient array of the POP. Then you choose a relaxation order, and you can solve it with the CS TSSOS first and the CS TSSOS higher. Now let's look at some numerical experiments. The first example is minimizing randomly generated sparse polynomials of the SOS form. We compare the performance of TSSOS with the globally polynomial and sparse POP. From the table, we can see that TSSOS is not only the most efficient tool but also the most scalable tool. The second example is minimizing randomly generated sparse polynomials with the simplex Newton polytops. We also compare the performance of TSSOS with the globally polynomial and sparse POP. Again, from the table, we can see that TSSOS is the most efficient and the most scalable among these software. The second example is the AC optimum power flow problem, a famous industrial optimization problem. We compare the approach exploiting only correlative sparsity and the approach exploiting both correlative sparsity and the turn sparsity. Here from the table, we can see that by exploiting both correlative sparsity and turn sparsity, the approach scales much better with the problem size. Indeed, the largest instance that can be solved with the TSSOS has over 6,000 variables and nearly 30,000 constraints. That's all for the talk. Thanks for your attention.